Hi, good morning. I'm glad to welcome all of you here, and I have the opportunity to introduce today's speaker, Dr. Janet Pierrehumbert. Dr. Pierrehumbert is a professor of linguistics at Northwestern University. She did her undergraduate work at Harvard. Then she had a Rotary Fellowship and spent some time in Finland before she went on to graduate school at MIT. She's done seminal work on studying intonation and prosody, been looking at the phonetics-phonology interface. She's one of the founders of LabPhone, which is an organization that looks at laboratory phonology. Been very instrumental in that movement and has been doing a lot of work looking at statistical cues with respect to word segmentation and the like. I don't know what else to say. And she's going to tell us a little bit about this today, and we're delighted to have her with us.
Well, thank you all for coming. Thank you for coming to what I take as an irregularly scheduled seminar. It's very kind of you to accommodate my schedule here and be here with me. Now, I'm a linguist, so I'm interested in implicit knowledge of language, what linguistic competence really is. And if you take phonology from a great phonologist like Morris Halley, in the introduction, he's going to tell you something like brick is a word of English, and blick is a possible word of English, although it doesn't actually happen to mean anything. And benick is not a possible word of English, as any native speaker can tell you. And this speaker's judgment of well-formedness is viewed as almost a direct tap into competence. Now, there's some assumptions here. Learning a language means internalizing some general principles, and these describe, in some way, the entities and well-formed combinations of entities in that language. So here I'm kind of scooting around the idea of a grammar. And that these general principles are revealed in productive behavior.
I'd like to understand this nick business. I mean, certainly English puts in words like refusnik. And we know what that is. It's Jews who want to escape the Soviet Union. And people use it. And if you can say D-N-I-K, then you can say certainly B-N-I-K.
Well,
and who knows what reasons would bring us to say nick.
In the course of the talk, I'm going to try to improve on this quite a bit. And I think as I improve, you'll see some influence of your work and some examples that are more in line with the ones that you bring up.
Okay.
Okay?
Right.
Okay. And the goal of linguistic theory, according to Halley, is to discover what sets of such principles may constitute a possible human language. And this is a goal I would stick to. What's a possible human language? We understand what's special about human language, why people can talk, and why they can understand speech, and the sort of deep regularities here. Now, you can ask, and I think quite a lot of us have been asking, what's the relationship of implicit knowledge to processing? And the stance I'm going to be taking in this talk is that the relationship is symbiotic. That is, knowledge feeds on processing. It develops in the course of processing over time, for example, through language acquisition. And also processing feeds on knowledge. That is, processing uses the structures which are set up in your long-term knowledge. And I would like to admit at the beginning that this is directly contrary to what I was taught in graduate school. When I was taught in graduate school, and we're now talking about the culture of MIT in the 70s, there's a strong distinction between competence and performance, and this is viewed as a kind of factoring problem in the scientific model. That is, you want, of course, a complete scientific understanding of language and everything connected with it. That's our sort of holy grail here. We approach that by factoring it into competence things and performance things. These are going to be sort of distinct theories. And therefore, you would see people running around saying things like, this is a competence theory, I'm not making claims about performance. Or you can disregard that fact because that's a performance phenomenon. I am taking the opposite stance from that here. Now, what do we know about speech processing, in particular, the decomposition of the speech stream. That is how we can decompose continuous speech. There are two factors here, which here I'm boiling down 1 million pages of articles into one slide. So excuse me for being crude, but one factor is that you decompose speech by spotting words that you know. That is, entries in your lexicon, which are particular words. When you observe a section of the speech that matches that, you recognize that it's there, and that implicitly decomposes the signal. Okay, now this is encapsulated in a huge class of lexical recognition models, lumping here all together. Ellman and McClellan, Norris, McQueen, Seidenberg, all of these models have this property. Now we have some fascinating results by Trusik and Aslan showing that babies recognize what I'm calling wordoids, even at 7.5 months. And the reason I'm calling them wordoids is babies have not mastered reference at that stage. So they're collecting some kind of inventory of sound chunks even before they know that these things refer to entities semantically. There's one very prominent probabilistic component in this area, and that is word frequency, which is generally translated into resting activation of the words. So words that you are extremely frequent end up as showing high resting activations or some analog of that, and that leads them to be recognized faster, with less errors, and under worse listening conditions. Okay, then we have another area, which is your general knowledge of sound patterns, including both prosodic patterns and phonotactics or constraints on phoneme combinations. And again, this has been shown both for adults and babies as a factor in decomposing the speech stream. And here we have a probabilistic component to watch out for, which is the observed pattern frequency. How common is a trochaic foot in English compared to an iambic foot? How common is an NT juncture compared to an MF juncture? This type of information. So to sort of structure the talk a little bit, I'm going to be looking at both well-formed judgments and some other traditional reflexes of implicit knowledge, and I'm going to show that they're sensitive to the same factors, and that they're sensitive specifically to the kind of probabilities I pointed out. And I'm going to start with point 2, that is part 2, your general knowledge of positional phoneme distributions. And then at the end, I'll come back to part 1, which has to do with effects of particular words. Okay, now the way I got into this myself was a long time ago, a LabFont 3 paper. I became curious about why you don't find words like pelskra. You ask anybody, this is not such a great word, they think it's the name of a Chicago alderman, okay? Indicating the strong Polish presence in Chicago. This should be, on a grammatical theory of syllable structure and word structure, this should be absolutely perfect because every subpart under any possible syllabification is well formed, and the junctures are all well formed. Okay, so we have words that end in ls as else. We have sk crossing the syllable boundary, ASCII. We have things like skidge, where sk begins the syllable. We have mask, we have crop. For every single subpart of this, you can find plenty of examples. And to make this point a little more clearly, right? If you take a grammar, such as prosodic word expands as cleaning plus on the syllables, and a syllable is an onset in rhyme. Now we know we have onsets up to 3 consonants. We have, even taking off appendices, we have rhymes with 2 consonants. So the allowable medial cluster should basically be the cross product of the final clusters in rhymes and the initial clusters in onsets. Okay, so my method here was to go through the Collins Online Dictionary, which has 70,000 words. I pulled out every single word that had 3 or more consonants, and I computed the sort of a priori likelihood of these clusters as a product of the frequency of the coda and the onset. Then the a priori likelihood of the cluster turned out to be the single most important predictor of what would occur. So let me step through this a little bit. If you run your grammar on word onsets and word endings, taking off the appendices, there are 8,708 syllabifiable clusters. If you look in the dictionary, there are approximately 50 that occur. That means 8,600 and whatever do not occur. Okay, what do we take as occurring? This is 10 years later. You should do a better job on this. This is extremely crude, but I just sorted them and read them and judged whether a reasonably familiar word had this cluster or not. And reasonably familiar, I was including words like pancreas, extirpate, palfrey, and doldrums. Okay, Velcro. You know, there's nothing wrong with the word Velcro. Okay, doldrums. Maybe you didn't know it, but you hear it. There's nothing wrong with it. But I did exclude Melanchthon, Riksdaler, Hoaxen, Anschluss, and Patzwallana. And a lot of people, I've gotten in trouble when I've given this talk before. Anschluss should have been up here. Okay, I made a mistake on Anschluss. Everybody knows Anschluss. And in monomorphemic, I included things which I judged anybody besides a linguist to view as a whole. Like there's complex, abstract, extreme, translate. Okay, now we estimate the onset and coda frequencies from the word onsets and endings. This is crude, but got us off the ground. We take the cross product multiplying the probabilities, that's independent random combination, rank them, and compare the rank list to the actually occurring clusters. Okay, here is the resulting graph that you get from doing this. And to make this graph, the ranked list has been bunched up in bins of 20. Okay, so here you have your first 20, your most likely 20 candidates, ranked 1 through 20. The next most likely, the next most likely. And you ask what percentage of this bin is actually found. So for the first 2 bins, we're at about 50%. The graph goes down rapidly after that. Once you're under the top 200, forget it. It's just not going to be there. Okay, so what this means is that probability alone is knocking out 8,500 clusters. Okay, if you put the probabilities in the grammar so that instead of just taking combinations, you're taking frequency-weighted combinations, then of course some of the probabilities are so low that you would not expect to find them in a sampling of 70,000. Right? You know, you get expected probabilities like 1 in a million, but we don't know a million words. We don't expect to find it. This factor alone knocks out 8,500 candidates, and the strongest phonological factor that's ever been proposed in connection with this, namely the nasal homorganic rule, actually only knocks out 70 candidates. So probability is way ahead of any grammatical factor, and I concluded from this that the probabilities are in the grammar, and that some of the other things we know are sort of built on top of them. Okay, now here's a paper which is in Press and Lab Font 6, and it's co-authored with Jen Hay and Ray Beckman. And this one is looking at the connection of processing to well-formedness in an experimental task. Notice what you saw, it wasn't an experiment, or at least the part I told you about wasn't an experiment. It's basically documentation of a systematic gap. So it's just like claiming that German lacks word final, voice stops. You know, we got to say something about that. But now we're going to have an experiment. And this was on the nasal homorganic clusters. So for this experiment, we made up by cross-splicing a set of 5 nonsense words, which are being varied in the medial cluster. And here you're seeing the log probability of the medial cluster from The most common one, having a log probability of minus 4.2 to down to log 0, which is, of course, undefined. These are impossible. And these were all made by cross-splicing. That is, even the good ones were made by cross-splicing to have a uniform quality of the stimuli, and they were all cross-spliced from cases where the original recording had a homorganic cluster. And we did this so that we could guarantee what the nasal actually was. Okay, notice if we'd said these, just said the nonsense ones, we would have had a risk of either over-coarticulating or producing disfluencies. But we didn't do that. They're all cross-spliced. And then subjects did two things at once. First, they these are block randomized now. They just transcribed the words, and then they rated how good they were as possible words of English. And so now we have two types of data to look at. One is the reanalyses. So you heard what was actually strimpy. What did you write down? And of course, quite often people write down MP rather than NP. And this is a very low-level perceptual effect. It's uncanny when you're working on this. You segment out your strim. You splice on your, you segment out your string, you slice on your P, you play it back. It sounds like strimpy. You say, oh my goodness, I made a mistake. I have to do this over again, okay? And you get up the spectrogram. You see that the spectrogram was really identical to where you thought it was coming from. It's really, really automatic. And what you're seeing on this graph is, this is kind of complicated pattern, but here we have the log probability of the cluster, and here we have the number of reanalyses that had that as an outcome. And the main point here is that this area up here, this upper triangular area, is blank. Okay, so you can reanalyze to MP or to NS, but there's nothing up here that's an outcome of reanalysis. Now let me put this with some numbers. We have 566 total reanalyses here, and we're going to split those into ones that improve, or improving in the sense that they reanalyzed a low frequency cluster to a higher frequency one, and ones that did not make an improvement. So your first point is that unlikely clusters are reanalyzed more often, with the result that the predominance of the analyses are upward in frequency. Okay. For the improving reanalyses, you're getting a pretty high correlation coefficient related to the probability of the cluster, whereas for the others, it's not significant. Okay? So the improving reanalyses, we have a correlation. The less likely a cluster is, the more likely it will be improved. But other reanalyses are random. Okay, now let's look at the Formanus data. And now here we have a very perplexing property. Over here, you might hallucinate this regression line here, but we have two cases of impossible clusters that were very highly rated. What's going on? And is what's going on related to the morphological analysis of the form? So here, people heard NP, they wrote down NP, they thought it was great. The question is, did they hear a word boundary when they heard the NP? So now we have a new experiment with a smaller set of stimuli, but a longer series, and this stimulus set has been increased to greatly have much better represented impossible clusters. And now we have the same task. And the reanalysis data came out the same, so I won't go over that. But now let's look at the Formanus data. Okay, so now we see that we were really onto a problem here, because these zero frequency clusters are spread out all over the place, and some of them are rated very, very highly. So now we're going to reanalyze the data on the assumption that we have three different competing parses going around. So people hear string P, what did they hear? One possibility is that they heard a monomorpheme along the line of pamper. So Zamper is like pamper. One possibility is that they felt that the word ended in two consonants, like the stem camp, and that we have a vowel initial suffix. And another possibility is that we have some kind of trochaic compound, and later I did find actually an example of a trochaic compound that's in the dictionary that meets this drum pad, which is used in electronic music as something for measuring the pressure on an instrumented drum. Okay, so then this would be an analysis of Krempich like drum pad. Okay, so now for each cluster in here, we compute all these probabilities. And now we're going to compare them and find out which analysis is the most likely given the cluster that was there. And here's a graph which kind of summarizes the nature of this comparison. And this is a little complicated, so if you're still lost after my explanation, you have to jump in at this point and ask some questions. Here we have the log probability on the monomorphemic analysis. That's the camper type analysis. Okay, now with two different plotting characters. Pamper, sorry, yeah, good, thank you. Okay, now here we have two different analyses that are being compared. The red one is the one across the word boundary, and the green one is the one with the vowel initial suffix. Okay? And that's the y-axis. Now, one thing you'll notice is that the range of values here, which is, since this is a square graph, that's the same as on the y-axis, is very large compared to the range of values for the red points. Okay? Now, what is the reason for that? That's because phonological structure is not our main constraint in combining words. When we combine words, the main constraints are semantic. So from a phonological point of view, you're talking about independent random combination, which is going to pull all the values towards the middle. Compared to independent random combination, the morpheme internal clusters, which are frequent, are extremely frequent. Okay, the ones which are bad are much rarer. So they're kind of pulled out around these middle points. So this means that the high frequency monomorphemic combinations, the winning analysis is going to be the monomorphemic one. Okay? For the low frequency, the winning analysis is going to be a decompositional one. And I believe this is a general true fact about language, which you will see reflected in a lot of studies about how transitional probabilities cue decomposition. Okay, now we take the most probable analysis, and the data is quite a bit better behaved. Okay, now everything has a non-zero probability, of course, since you can have anything across the word boundary. So we're moving everything over here, and we're getting an R squared of 0.65. Now, when we looked at this, we realized there was an uncontrolled factor in our experiment. So now we're into a post hoc observation. And that was whether the cluster contained a strident or not, which was interacting with the stridency in two of the stems. Okay, so Strimpy and Zamper has a strident coronal. And we've got these clusters, M, Sh, MS, and Sh, and so on, that have strident coronals. So we think there might be a OCP effect on that. And sure enough, if you split apart by the stems, there is actually a difference. The ones containing the strident coronals are coming out worse, and I'll show you. This will be a little more transparent on the slide. Okay, here's what happens if we put two regression lines through separately for the clusters containing a strident coronal, which were now being generally disfavored because our stems, 2/3 of our stems had strident coronals, versus the other ones. Okay, and that looks pretty good. And one thing I'd call your attention to here is it looks like we have now we have a cumulative effect. As far as this resolution of this data set goes, we have a effect of the log probability of the parse on the cluster we were looking at. So that's an effect related to the probability of the nasal obstruent cluster. We have an effect related to stridency co-occurrence, which is showing up this way. Okay, and since these lines look parallel, it looks like we have a straight cumulative effect on the well-formedness of those two aspects of the phonology. Okay. Now, moving along to another cumulative effect. A few years ago, I worked with John Coleman on a post hoc analysis of an experiment he'd done, which was on psychological reality phonotactics. So people were rating words like rupation and listless, where rupation has an impossible cluster. And this study had a perplexing outcome, which we wanted to follow up. And that was that some of the words with completely impossible clusters were rated much better than ones which were good everywhere. Okay, so you had some words, nonsense words, which he designed to be well-formed. Every bit of them was well-formed. They were nonetheless rated pretty low. And then some of the ones that had impossible clusters came out with very high ratings. Now, why is this a problem? On a standard phonological theory, and that includes many different versions of generative phonology, if your parse bombs out anywhere, the parse of the whole word is bombed out. It's impossible. There's no way that good parts could offset bad parts and add up to a good overall impression. So, to analyze this data, we developed a stochastic parser of the English lexicon. This is done on the OED dictionary, the Oxford English Dictionary. And it covers English and foot and syllable structure down to the onsets and rhymes. That means the onsets and rhymes are viewed as holistic units. There's no internal decomposition. And we tabulated frequencies on route to frontier paths. And we provided a small, but non-zero frequency for unattested clusters using an interpolation formula called the Good-Turing formula, which basically ends up giving them low counts, in fact under 1, but still positive. What is a route to frontier path? Okay, here I have sketched out, this is the word candle. Okay, candle, of course, is a strong syllable followed by a weak syllable. This is a word, and here it's a self-contained utterance. This is going to start at the root of the tree and track down the tree, preserving all the labeling until it picks up this rhyme. Now, this rhyme is, of course, medial in a word. Here we have the word can. This path is practically identical, but it's word final. So that's going to be a distinct route to frontier path. And this is different for people who have some kind of computational linguistics background. This is different from stochastic context-free grammar, which would put probabilities on the nodes. So if you had probabilities on strong syllable as an expansion of KN, these would actually come out the same. But they're coming out different because of their temporal location. And then we zip these all together horizontally to get the probability of the parse. So what this is, and here's where I owe a lot to Fred and his colleagues, this is a Markov model over the route to frontier paths. Okay? Not just over the phonemes, but over the entire labeled position of the phoneme. Okay, so one thing I'd like to point out from this is that for any given onset and rhyme, the probability proved to be wildly different depending on its position with respect to the stress of the boundaries. So for example, STR is immensely more common as a word onset when the onset of the word is stressed than when it's unstressed. And I don't think there was any elements in the top 10 that were even the same. So if I could pontificate a little bit to psychologists, it's that you want to be careful about viewing prosody and phonotactics as separable factors, and I think maybe about some kind of positional contrast or licensing theory here. Okay, now we found that the overall parse was a highly significant predictor of well-formed judgments. That doesn't mean it was highly effective. It was highly significant, but highly effective, and the effectiveness problems came about because there was a fantastic amount of noise in these stimuli. There were, 15 extraneous factors that I would never have put in there if I had designed it for this purpose. Okay, but it did actually manage to capture the fact that some words with illicit strings are highly rated compared to ones which are fully licit, and they're rated that way by virtue of the rest of their composition. Okay, so if you have a local cluster which is bad, the rest of it's fantastic, you could end up with an overall high rating on this type of parsing. Also it makes a very strong prediction which appears to be correct, and that's that longer words are cumulatively bad. Okay, the longer you get, the worse it gets. And that's because the longer you get, the more states you put on, and each state has a probability under 1, and so unless you do something to normalize the scores, by gum, it's going to get worse and worse. Now, this prediction was actually published in Chomsky and Miller's article on the cognitive implications of Markov models. That was back in '61. So my verdict on this is that Chomsky was onto something at that time, and that the people who followed this up were wise to follow it up. The fact that Chomsky abandoned this point is perhaps unfortunate. But. Okay, now, what's the problem with length? If you just take a simple grammatical model, words of the longest length are going to dominate the lexical inventory, wherever you cut off the length. So, okay, we all recognize the Kleene star doesn't really mean Kleene star. We don't have words of infinite length. We just chop off at 3, say. Okay, now if you had 1,000 syllables, 1,000,000 disyllables, 1,000,000,000 trisyllables, and you do a random sampling of that to get your lexicon, you're going to get 100,000 trisyllables, 100 disyllables, and 0 monosyllables, right? This is false. A big online dictionary has something like 13,000 monosyllables, 31 disyllables, and it really goes down from there. Now, Frisch, Large, and Pizzoni did a pretty careful follow-up on this length prediction, which is in Press and JML, where they made words of 4 different lengths containing high frequency and low frequency components. So the actual lists are much longer. This is just to give you a sampling. And then they had people, and now here's the predicted likelihood of these words. Okay, so we have 2-syllable, 3-syllable, and 4-syllable words. The high-frequency parts, of course, give you more likely better overall scores than if you have low-frequency parts. The more high-frequency parts you have, the worse it gets. But the low-frequency ones get worse faster because all the parts are so low-frequency. And in particular, you'll note that 2-syllable low-frequency words have almost the same score as 4-syllable high-frequency parts. And now you have people rate these. Despite the bar coloration, which they seem to have reversed high still on the left here. Okay, so high-frequency ones are rated better than low. Shorter ones are rated better than long. And sure enough, the 2-syllable ones with low-frequency parts are rated pretty much the same as the 4-syllable ones with high-frequency parts. Okay, so this prediction was really extremely well borne out. And I think it is the case that long words need to be locally better to be there at all. And that's why so many of your weird combinations like dwarf. Okay, DW is a very rare onset that only shows up in a few monosyllabic words. Okay? Okay, so here I've reached the end of the part I'm doing on nonsense forms covering general phonotactics. The conclusions I'm coming to, and this is a little reckless, this is kind of saying where things are going. First of all, I think well-formatist judgments are gradiently related to the statistics of lexicon, so that the same statistics end up impacting both well-formatedness and low-level speech perception. Okay? And that's because both your sort of meta-linguistic judgments and the speech perception are kind of projected off the lexicon through your experience with words. This doesn't say the same box is doing both, but both boxes are influenced by the same experience, which is experience with words. And of course, even the little babies, they may not know they're listening to words, but they are listening to words. So the probability distributions that they're hearing are affected by what is actually in the lexicon. And I think the perceived likelihood for the parse of a complex form is a cumulative function of the likelihood of the parse. Now, there's one little point in here which is great for OT, and you might have noticed it, and that is that when we were rating the nasal homorganic words, the rating is controlled by the single best parse. Okay, it's not that you take all three parses and average their scores together to get your rating. By God, you heard it one way. It's like a necker cube, you know? You heard it concave out, you know, you're concave in, you know, you see it one way, you see it the other way, that's what you saw. And then given that that's what you saw, you have an impression of how good it was. Okay? And I think that's one reason that one of the most active and successful areas of OT has been prosodic parsing, right? Where you have competing prosodic parses for some material which have a lot of repercussions, and by gum the best one is it. Okay, now moving along to a couple of properties of actual words here. Now we're going to bring in some results that involve actually having a lexicon, where you know, some words are there, and that influences the decomposition. So let me remind you that when you hear a word such as maladapted, you have to recover two structures at once, and I've deliberately picked a word here where they're very decoupled. Okay, on the top, sorry, I've put the phonological structure. This has a syllable structure. Maladapted. Okay, this is on a strong, weak trochaic pattern. Maladapted, that's the foot structure. Now we've got a word. But meanwhile, this is also a stem, adapt, with a suffix past tense. That's making up a verb, which was turned into an adjective by a zero derivation, and now we got this prefix on meaning badly, so that gives you this other tree structure. And you can see that these are sort of decoupled at every level, both in terms of the bottom boundaries and in terms of the form of the tree above that.
Excuse me, the bottom parse, this is a usual parse. In other words, you could write a grammar which would have that adjective is prefix plus adjective is verb and all that sort of stuff, and that would generally hold for the English language. Is that right?
Well, this would be the morphosyntactic part of your natural language system, right?
Yeah.
Now,
So
if you're looking at,
this
you know,
is
if you were trying
universal for
to,
English,
this is for English, yes, yeah,
and would be quite valid.
yeah.
I'm not doubting it. I'm just asking questions.
Yeah. So are you?
Well, I'm wondering whether, you know, I mean, normally, of course, when we write a grammar, context-free, etc., we use words as units. So we would have maladapted as an adjective, period. And I'm wondering
yes.
whether we could, in fact, get a grammar that's that way, and we would not have words, but we would, the grammar would continue to morphemes. And
Well,
that way we would reinforce you know, certain morphemes which are probable and etc.
Yeah, I think, there's some very interesting work on this area, especially on languages with extremely productive morphology. So for example, if you want to do, a spelling corrector for Finnish or something like that, which has a vowel harmony rule that will span some highly productive suffixes, like the possessive suffix.
Right.
You have to have some morphological decomposition because you can't expect to have gotten every single word in the language with a possessive suffix on.
Well,
Now,
I mean,
there's
in German,
some
where
issues
there
I'm
are
going to come-
compound words, right?
Yeah,
I mean,
yeah,
we should
yeah.
have that because there are compound words which are very infrequent, but they are composed of things that are quite frequent. And,
Yeah. I think maybe you're anticipating some of the issues that I'm going to raise, so we'll come back to this,
Right.
okay? Okay, now, the earliest models that handled what actually is in the lexicon, an example would be Elman McClellan, 1988. This is a very early model, which has what I call in situ phonology. It has no phonology as such. Basically, you've got the speech coming in. It's you have a lexicon. It's activating different parts based on the match, and the winning candidate is the one that has the cumulative activation of all these parts.
it has
And furthermore, what?
Just say it again. I didn't.
Okay, so our winning candidate here is bet.
Yes.
Okay, here's a B, here's an F, here's a region of glottalization representing the glottalized T. Okay, when speech is coming in now, here's the voice stop B. That's activating the B of all these three competitors here, bat, bet, and bed. Okay, now here's the vowel coming in. Now bat drops out because the vowel fails to match. Okay, now bet and bed are still about equally activated. Now we hit this glottalized region, and so that is interpreted as a glottalized T. And so now bet is the most activated, and of course in some versions you would also have mutual inhibition here, with the result that not only is this activated, but those are actively suppressed by being inhibited. Now, more recent models actually have a more explicit manifestation of the phonology, and I'm going to call that a fast-phonological-Preprocessor. Okay, so now the speech is coming in, and here now I'm working on something like horn button. Okay, here we hit the NB juncture. That's impossible within a word. So the system analysis system, as a general property of English, is imputing a word boundary there. Okay, that's enough to project B as a syllable onset. So now we're activating words which all start with B. Okay, now we come into the vowel. We've got our vowel. We know it's a strong syllable because it was so nice and long and pitch contour, all that jazz. So now we're still good with all of these. We get this glottalized region here. That's not a flap. So the syllable beginning with these are still both activated, and as soon as we hit a syllabic N and recognize it as a syllabic N, then we know that that was not a T at a word boundary, and the reason is because syllabic Ns don't begin words in English. Okay, in a word like enforce, you have a schwa, whereas in button, the schwa could be completely gone. So it's trained up on that and is putting up the analysis that will get us to button. Here are some reasons to believe this. One is a very cute series of experiments by Pitt and McQueen, which showed that phoneme decisions are biased by transitional probabilities, independently of specific lexical entries, even after the unique point of the word, indicating that even after you've recognized the word, this thing is still doing its little stochastic job. Then we have some experiments by Vidovich and Luce, showing task dissociation between transitional probability effects and lexical neighborhood effects. And the in situ type model cannot really accommodate these results. Here's some more reasons. These are a little more speculative. But one is it looks like infants develop a language-specific speech decomposition before they actually have a lexicon, in the sense of having reference. And indeed, it helps them get their lexicon. So if you just leave that in place, there's a sort of foundation for your Fast-Phonological-Preprocessor, and getting rid of it would impute a kind of massive reorganization to the child. And evidence against this massive reorganization is that some experiments by Terry O on people who had only early exposure to a language, this is like 2 years and under, and then they resume learning it in adulthood, and their progress on the language is immensely facilitated. So for the, for example, for the Hindi dental retroflex distinction, they're able to learn that and relearn that in about 5 weeks, whereas for people with no prior exposure to Hindi, it's about 2 years. So that's a big advantage and suggests some real permanent structure being laid down there.
Yeah, does that extend to production or only to perception?
Good question. I believe it extends to production, but maybe Peter remembers the article. Yeah?
Yeah, I think it extends to production.
Yeah.
It would be hard to separate them. I imagine it's much easier to tune your production up if your perception's in place.
Yeah, I mean, of course, there are cases where people could do perceptual judgments but cannot reproduce it, right? So there's some, but I believe this also extends to productions, yeah. Okay, so now let's consider what's going on with complex words, like maladapted. Okay, now here I'm going to buy into dual root models, okay, which have a whole word root. This is maladapted, stored as an entire unanalyzed unit without anything inside it. And we have a parsing root, which is an access to the whole word through the morphemes which make it up. Here's some people who were arguing for models like this, and the assumption will be that these two roots operate in parallel, and whichever root finishes first will be responsible for lexical access on that occasion. If the parsing root is the only root, it's obviously going to finish first. And now the speed of the whole word root is going to depend on frequency. Okay, so practice gives you speed. So high frequency complex forms are more likely to be accessed by the whole word root than low frequency complex forms. Okay, so here we've got maladapted. Here we have our lexicon, which now has its sort of additional structure, giving you two ways of getting here. The analysis is the same. Here we have a kind of, in this particular example, sort of decoupling between the phonological analysis and the morphological analysis, which is presumed to slow you up on this decomposing route. Here we have the interstate, okay, which is bypassing our business district here and zooming us straight to the end. Okay? But now let's look at something else like malpractice. Okay, here the syllable boundaries actually are aligned with the morphological boundaries, which is going to facilitate the decompositional route. So the decompositional route might win more often than it did with maladapted. A key assumption is that the long-term representations of words reflect the way in which the words were accessed. So if a word was accessed by the decomposing route, this is going to be reflected in the internal structure in the lexical entry. Sort of like a context-free grammar builds a tree during a parse, and then that tree is a kind of relic of how the parse was achieved. Okay, same general idea. So this means if the word is accessed in different ways on different occasions, we want to have some kind of implicit probability distribution over the alternative structures. Which of course you could do very easily using some kind of exemplar model. But there are various other ways of doing it. Okay, now what kind of properties would follow from this? And one property has to do with word-specific effects. And here I'm going to be sort of plunging into an advertisement for Jen Hay's thesis. She's just finishing up her thesis. Let me call your attention to a distinction that she's making very clearly, I think more clearly than any of the prior literature. And this is the distinction between absolute frequency and relative frequency. Now, we've already kind of seen this implicitly for phonological pattern frequency. So you could say the absolute frequency of n.s as it occurs in 91 out of 11,363 monomorphemes, that gives it a certain probability. However, when you're looking at a competing parse, now you're talking about a relative frequency. So we have ns in something like fancy versus ns in vancy. Okay, a given ns that we hear, which one is it? Now we're talking about a relative frequency. What's the comparison of this analysis to that analysis? Now, you have the same thing within morphology for word frequencies, frequencies of individual words. So an absolute frequency of insane is 258 out of 18 million. But now we can compare the frequency of insane to the frequency of its base, sane. And insane is actually more frequent than sane. It's about twice as frequent. Okay, so remember our little assumption that frequency translates into speed. That means that in cases where a component here is extremely frequent, that's going to speed up the decomposing route. If this is relatively infrequent, this route is more likely to win. So here are now two experiments showing that relative frequency has its hallmarks in some kind of classic evidence of implicit knowledge. Okay, and insofar as we can show that relative frequency shows up in tasks related to implicit knowledge, we have an argument that this word-specific probability information found in the processing model is relevant to competence. So here we have, this is based on pitch accents under focus, as in the example. This whiskey wasn't exported, it was deported. Famous example from Bollinger. Okay? Now, the hypothesis is that focusing the prefix is more possible if the form is showing up decomposed in the lexicon. Okay, the more the form is decomposed in the lexicon, the more the prefix is an identifiable unit, the more it is likely to bear focus. So the experiment has 14 matched pairs of prefixed words. These are matched for the identity of the prefix. They're matched for the syllable count. They're matched for the phonotactics across the morpheme boundary. And they're matched for the absolute frequency of the derived form. And don't try to run this experiment on more than 14 pairs. There are only 14 such pairs in English, okay? This is, okay. And now we're embedding these in the dumbest possible focusing environment, okay? Sarah thought the document was legible, but I found it completely illegible. Versus, of course, they could say, Sarah thought the document was legible, but I find it completely illegible. Sarah thought her cousin was liberal, but I found him completely illiberal. Or did I find him completely illiberal? Okay, so randomized together, filled with sentences, filler sentences given to subjects. And prefixes on words with a derived form more frequent than the base were significantly less likely to attract a pitch accent. So here's the graph showing that. This is the difference between the log frequencies of the base and the words, and this is the difference in number of tokens with an accented prefix. So it's a pretty good relationship there. Okay, now there's also a connection to level ordering, which you all know about. So going back to Siegel, we find that some suffixes, such as E, 8, ID, and so on, generally attach inside other suffixes. with the result that you get words like biliousness, where the more the vowel initial and less productive suffix is inside the other one. Now, level 2 affixes are more productive generally. They're more semantically transparent. They tend not to impact the phonology of the stem, and they tend to begin in consonants or create other cues to juncture. This is kind of syndrome of the level 2 affix. This is extremely controversial area of phonology. So here are a couple of problems. One, why do these factors go together anyway? And if you have a purely grammatical account of phonology, you would encode the fact that they go together, but you wouldn't have a way of encoding it really very well, or even let alone explaining it, and that's because of the reference to substantive factors here, like actual meanings of words and actual phonetic substance. And then there's a big problem with ordering violations. That is, these tend to occur in this order, but not necessarily. They're sort of fringe of examples, and as soon as you allow any of the counter examples, you're basically predicting that they're generally possible. Now, here's the predictions of the dual access model on this. You basically predict that highly separable affixes should attach outside of less decomposable affixes, and the reason is if you get a parse like contain and then plus and then mental, this is now supposed to be contain ment plus the affix LR, this would lead to encoding errors during lexicalization. So we have phonotactics as a general effect on decomposability, leading to the observations about the character of these affixes. But we also have word-specific effects on decomposability, namely relative frequency. So we're expecting now that the supposed lexical exceptions to level ordering should actually correlate with the relative frequency of the base and the stem. And here's a pilot experiment that she's running on a full scale probably right now. Made a lot of neologisms involving ul on mint. Okay, this is a classic example of level 1 affix attaching outside something that's mainly level 2. Okay, so we're looking at discern mental, contain mental, derange mental, agree mental, import mental, appoint mental, punish mental, and invest mental. Okay, and here's our log relation of the base to the derived form, that is to the munt form. Up at the top, we have the base more frequent, that is discern is more frequent than discernment. Down at the bottom, it's the other way. Investment is more frequent than invest. Okay, so up here, we're predicting a rather strongly imputed boundary, whereas down here, less so. And sure enough, that showed up very strongly on the ranking of these forms. That is, people agree in ranking as poor the forms for which the verbal base is higher, and they agree in ranking the ones in which the base is lower frequency as much better. Okay? So this not only explains the cluster of counterexamples which actually occur, but it even explains extension on a productive task. And then the last general point I would make is a sort of hallmark of language is that morpheme boundaries, that is the boundaries in things like malpractice for decomposing morphology, are kind of like word boundaries. Now, you wouldn't have to have a language be like that. You know, just from a mathematical point of view, you could design a language in which there was one battery of cues to a word boundary, there was some other battery of cues to a morpheme boundary. In some ways, it would be even a better language, because then you would never make any mistake about what was a morpheme boundary and what was a word boundary. If you do your most simple-minded type connectionist simulation, and this is now Hay calculating a simple recurrent network and it's trained to spot word boundaries, and then you're looking at how it tests out on morpheme boundaries. The result here is that the learning extends naturally to morpheme boundaries, but in a sort of attenuated way. Okay, so a training that is 89% effective at spotting word boundaries is hitting 60% of the word internal morpheme boundaries. And I think this is a general fact about language, that morpheme boundaries sort of act like weak word boundaries, and that follows from the kind of architecture I've been talking about. Okay, now that's the end of what I have prepared here. So I guess my conclusion is that probabilities are inside the grammar and you know about them, and that when you have, but that you nonetheless get absolute effects in the sense that when you're parsing a whole form and crossing levels of analysis, you get single candidates winning absolutely. Okay, so we need to think carefully about when we expect cumulative interactions and when we expect winner-takes-all interactions. And also that you do get hallmarks of actual processing of individual words in kind of classic areas of phonology. Thank you. Yeah.
The phonological fast phonological preprocessing
Yes.
went by a bit too fast for my preprocessor or something.
Okay.
The post-processor.
Yeah.
Could you just, verbally describe what it does, and maybe more interestingly, what you think it doesn't do?
Yeah. Let me put up the slide again, just to have some things to point to. Okay. Now, one reason I'm being sketchy about this is because of differences between what I suspect and what the proponents of these models are actually doing. Okay, so let me first kind of say what they state, and then say what I think is the likely line of development. Okay, so people, we're talking about models like shortlist, in which the speech is presumed to be analyzed bottom up into some kind of fine categorical transcription. And then based on general facts about transitional probabilities and stress, some decomposition is imputed to this phoneme string. Okay, so for example here, under shortlist, my understanding is they think you would get the M, they think you would get the B. Given that it was an NB, it would have to have a word boundary because NB is impossible word internally in English. Okay? Now, the automatic speech recognition literature suggests...
The impossibility of NB is not an emergent property of the lexicon.
Well, no, it would be an emergent property of the lexicon. I mean, these things would be trained off the lexicon, right? So in a language, in fact, they have done experiments on language particular differences. So for example, in Dutch, NB is actually possible. And you're getting hallmarks of that in reaction time experiments and things like that. They did there's a study by Otaka and Cutler comparing Dutch and Japanese, where Japanese has a very strong nasal homorganic constraint and Dutch doesn't. And we're now looking at, reaction times for phoneme monitoring on the nasal. Okay, and you're getting a difference, basically. The Dutch people are paying much more attention to the nasal. And you might say entertaining, my understanding of this result is the Dutch people are entertaining the hypothesis that this might have all different places. Okay, and that shows up in their type of experiments. Now,
excuse me real quick.
Yeah.
So are you assuming then that the training would be like you fix some sort of lexical analysis and you're training up the preprocessor representation report to mediate between the speech stream and the lexical representation? Or
For all I say, it would be like that, right? Okay. Now, as soon as you say that, you know there's some problems, I know there's some problems. That doesn't mean I think they're completely wrong. Okay. Now, one problem is, of course, the kids seem to be getting this before they have a lexicon. Right, so we need some kind of acquisition bootstrapping story, which I think they would be the first to admit. Another problem which they will admit is these boundaries are not actually hard. That is, their model treats it as basically possible, impossible, whereas the evidence suggests that there's some kind of perceived boundary strength, which is probabilistic, and you really want to be returning a probabilistic boundary here. Now, if I talk to McQueen about that, he kind of says, yeah, you're right, that's the obvious way to go with this. Okay? Now, the other problem, which I think is very severe, is the actual assumption of the categorization of the signal into phonetic transcription. And if Fred was here, he would tell you this is a horrendous problem, and automatic speech recognition systems that try to do that bomb out, and the reason is because they get hard errors. That is, if they make a mistake in analysis at this point, it's fatal. Okay? So personally, I don't believe that bottom-up phonetic transcription is possible, and I don't believe that people do it. I think there are two ways that this might play out as far as this level of analysis goes. Okay, one would be where this comes out like an annotation on a spectrogram. That is, if in your spectrogram reading class, you're marking up your spectrogram with stress marks and broad vowel classes and all kinds of stuff. But when you try to decide what the sentence is, you look at the whole spectrogram plus your annotations. Right? So one possibility is that this analysis is just decorating the speech, and then the whole shebang goes up. Okay, I think that's kind of my favorite. Now, another favorite, which might be suggested, I guess, by people like Victor Zhu, is that this is not as fine as all that. It's doing some kind of broad, it's doing only the analysis that you can do bottom-up. So, for example, major class of the vowel, you can do bottom-up quite reliably. Syllable structure, back in the early 70s, there were already syllabification algorithms that were like 98% correct bottom-up. So you could do syllable count, okay? And that then that is pulling out a cohort from the lexicon, which is then compared in more detail to the speech signal. Okay, that's the other sort of class of model I know about that might be an avenue. But personally, I think it's probably an annotation of the signal, and a lot of quantitative information is also going up. Yeah.
The interesting thing about this is that Gagan and Luce have some data looking at sort of peaks and troughs, for recognizing these things. What they find is that you get, you seem to use the phonotactic information at least enters into the decision process at the onsets of the words. But contrarily, on the offsets of words, subjects tend to be faster for things that are good phonotactic continuations as opposed to, what you might expect. I mean, the initial hypothesis that they had on this was that we would get troughs at both ends of the word.
Oh, sorry, what's the task?
Well, it's a variety of tasks, but it's basically a monitoring task where you're looking for a particular element, and the sequences are CVC, CVC, CVC sequences, okay? And they're manipulated in their...
and are you looking for a CVC or just for a phone?
You're looking for a CVC.
Okay.
Okay,
yeah.
so you're looking for a CVC that could be a word, and they're actually paired with non-words and stuff like this. So you're basically searching for a word in the task. And the data that they focus on mostly are those where they're embedded in the middle, because they're interested in seeing what kind of boost you would get from having a consonant sequence that occurs with much greater probability across words than within words, for example, right? And so what they find is that the subjects are actually fastest overall, if you look across all the conditions. They're fastest when you get a good trough at the beginning of the word, but where you actually have a good continuation on the offset of the word.
A bad trough.
Yeah, not a bad, right, a bad
Good
trough.
trough at the beginning, bad trough at the
Right,
end.
right.
So what
Which
are
they
the,
argue is, it's a lexical competition effect on the end of things. But what seems to happen, at least for their subjects, is that they seem to use the phonotactics in the beginning, but not so much at the end, because by then they're overwhelmed by influences from the lexicon.
Well, there's a kind of analog to that in Frisch's results on similarity in speech errors, okay, where if you're looking at rate of speech errors by prosodic position, okay, the error rate is dominated by similarity at the beginning of the word, but the contribution of the similarity to the error rate is going down as you go through the word, presumably because the cohort effects in terms of recognizing the actual word are kind of taking over, right? And governing the class of intruders.
Right. Now, the interesting thing for us with babies is that Mantis and I have found that the infants, when they can use phonotactic at 9 months to isolate the words in fluent speech context, are actually just as fast if the information occurs at offset as if it occurs at onset. So they seem to be relying more heavily on that sort of thing, which in a way is what you would expect, given that they haven't built a big lexicon yet. So that, you were talking about how you would transition into this sort of thing. And it looks like, they're using much more low-level information initially.
That's really interesting, yeah.
That's in that one of those papers.
Yeah, good, thank you.
I think that throughout the whole talk, I've been really confused about what you were considering as word boundaries and what you were considering as morpheme boundaries. Because at the beginning, and I might have just missed this, but so I thought of a whole bunch of words that have NP clusters in the middle, and then you talked about how actually these things do occur, but you didn't talk about them in terms of morphology. So, and then it came up again with this. So I thought, well, you could have unbutton or input, or unplug, things like that, that are morpheme boundaries at the beginning of words, not even compounding. So your drum pad example was more an example of compounding, and it just made me wonder, so in the case of the Fast-Phonological-Preprocessor then, why does it have to mark that as a word boundary there? It could be a morpheme boundary.
Well, I mean, that's, I think that gets exactly back to the point which I maybe went over too fast. Under this kind of architecture, you get a heavy confound between morpheme boundaries and word boundaries. So that, you take an extremely productive prefix like un, in the linguistics literature that will show up as a word boundary prefix, thanks to the fact that it has the phonotactics of compounds and that you get completely decomposable meaning. So if you parse that, you basically parse the parts, you put them together compositionally, bingo, you have your complex word. And then the problem has been that there's this kind of uneasy gradation between from that to the less productive and more incorporated affixes, like serene, serenity, where the syllabification crosses the word boundary, the stress pattern is shifted. You can get idiosyncratic meanings kind of taking off. In fact, a wonderful example of this was just given to me by, I'm working on designing a new experiment in this area. I was scrounging around for examples, and it turns out that in the dialect of our grad students, the form high octane has taken off as a high frequency independent word, okay? So here we have the compound high octane. There's basically no problem with that juncture, really. High octane? Okay, so without the glottal stop, it's taken off just meaning high powered. And you can say things like, I hate it when high octane telemarketers call me up. And that's a very sort of, typical thing that can happen to an individual word if there's no phonotactic problem, or and the meaning happens to be something that's, becomes fashionable. And you actually even see kind of leniting processes exactly targeting phonotactic violations in words that might have a morpheme boundary. So you look at the rate of T deletion and say swiftly versus daftly. Okay, swiftly, the T is more likely to get deleted than daftly. And that, is cleaning up the juncture. I think most linguists would put a word boundary and would view, and and have that extreme of word boundary morphology, which is supposed to be sort of like syntax, highly transparent, compositional, and productive. Then we've got this other extreme, and the theoretical fight has been about how to characterize the continuum, which seems to fall, traverse the space in between as you look into the effects in more and more detail.
Yeah, I had just a clarification question about the experiment where you said there were competing prosodic parses.
Yeah.
That the subjects were assigning.
Yeah.
Subjects were choosing one. That wasn't explicitly tested by the experiment, right?
No, that's implicit. It's a competing morphosyntactic parse. Okay, all of these were prosodically
That's your
the same up to maybe the level of whether there's a prosodic word boundary or not. But they were all trochaic, they all had the same junctures, they were the identical same tokens. And now the question is, what is the morphosyntactic parse? And we did not ask them whether they thought it was a compound or not. Okay. So I just asked them, how good is this as a possible addition to the English vocabulary? Of course, you don't mind adding compounds to the English vocabulary. We add them all the time. There was no direct tap on what they thought the analysis was. And it, I think, would be worthwhile to do some sort of follow-up where you, I don't know, asked them to hyphenate or something like that, looked at some sort of more overt reflex of what they thought the analysis was. Yeah. But, compounds, of course, since these are trochaic, they're on the pattern of catfish, which wouldn't be written with a space. But it would definitely be worth following this up with a more direct, or additional, at least, measures into their analysis.